Hello, everyone. Wait just another minute and a half or so for others to gather, and then we'll get started. Thanks for being here. Let me know if you can hear me / see me. This is a new setup for me here on YouTube and everything. So I'm hoping that things go well. Excellent. Glad to see our Silicon Society friends here as well. Thanks for supporting. I'm just going to close out of some windows I have open. That way, stream takes up less of my computer's RAM and hopefully get a smoother stream. Cool. Alrighty, that is time. Glad to have you all here. The first thing I want to mention to you is that if you want to get in touch with me during the next hour or so, the best way to do that is through the YouTube chat. And I'll be sharing some links and other important materials with you there as well. The first one I want to share with you is just this short survey so I can learn more about you, about what your goals are, what your background is. It has some really basic questions. Shouldn't take more than 2 or 3 minutes. So I'll paste that in the chat so I can go ahead and close this browser tab. All right. Oh, it started me at the end of my presentation here. Okay. Welcome, everyone. First thing I want to mention is my name is Ryan Allred. I'm the founder or proprietor of temsy.com, a website where I hope to teach others data science, machine learning, artificial intelligence, etc. And I've been teaching individuals data science and software engineering for the past 10 or so years now. So I've got a lot of experience teaching these topics, particularly teaching beginners and helping people get from zero to hero, zero to becoming employed data professionals is some of my background. And so today's stream is the first of what I hope will be many machine learning workshops that I can have with you to teach you some of the basics of machine learning. This week in particular, we'll be hitting on some particularly introductory topics, but as part of that form that I shared, there's an opportunity for you to say some of the topics that you are interested in, things that you want to learn about. And if you have a particular topic that you're aware of in the data science space that you really want to master, you can let me know. We'll kind of take it a week at a time, planning 2 of these workshops, Tuesday and Thursday sessions. And so next week's topics are still to be decided. So let me know what you want to learn about. Okay. Today we're going to talk about just an introduction to machine learning, and here's some of the basic things that I hope that you'll be more aware of by the time that we're done. First off is just some terminology, things like models, algorithms. What is a prediction? What is tabular data? What does it mean for a model to generalize? And what is a target in our data, or what are the features and attributes of our data? And we're also going to cover briefly the 4 major categories of machine learning algorithms, machine learning models. And then very quickly, because I don't want to ever have one of these workshops where we don't dive in and write some code, we're going to try and do a little bit of a hello world example of what it takes to load a data set, train a machine learning algorithm on it, and get some predictions out of it. And that will be, I think, one of the last things we do. Right, Cigar says he's from Virginia. Bonosa1 is here from Florida. If you have any questions at any time, type them in the YouTube chat. I might not answer them at that exact moment. I may wait until we get to a place where we can pause, but feel free to ask questions or comment at any time, and I'll keep an eye on it. Alrighty. So, what is machine learning? Well, it has the word machine in it, right? So I want you to imagine a machine here with me. This machine here in particular is for making bread. Now, the exact machine in this picture doesn't actually make bread. All that it does is it takes in dough in this receptacle over here and then divides it into evenly sized balls. So all it does is divide up dough, this giant thing, okay? But imagine that this machine did it all. Imagine that it could mix the ingredients, bake the bread, and spit it out on the other end, okay? Well, the machine can't do it on its own. It needs some inputs, things like flour, water, salt, yeast. I put 3 of them here, but it needs ingredients. It needs inputs going in to make the bread, and hopefully out on the other side comes some outputs, some beautiful baked bread, right? And that's really what a machine is. It's something that takes inputs, modifies those inputs, and spits out an output. And that's really all that our models and algorithms in machine learning are doing as well, right? We can take that machine in the middle and switch it out for, this is a diagram here, very basic diagram of a neural network, right? A type of machine learning model, machine learning algorithm, and it also takes in inputs and spits out outputs. Maybe not literal physical inputs and outputs here. In the machine learning world, the inputs we call data, and the outputs we call predictions, right? And the whole goal of machine learning is to make good predictions, right? Just to make as good of predictions as we possibly can, okay? But there are some big differences between our bread making machine and our artificial intelligence machine learning algorithm machine here. They do a couple things differently. And I want to kind of use this bread making analogy to give you an example of how a machine learning algorithm might try and do a task, right? So I want you to think about having a machine, right? And imagine you had to build this machine from scratch that would bake bread. What would you do? You'd dive into the internals, right? You would make some kind of a vat where the ingredients could be mixed up. You might have a container for the dough, an oven it can be baked in. You'd have to go in and you have to specifically add to it all of those components so that it could do what it wants to do. Well, the biggest difference between machine learning models and literal physical machines is that once we turn them on and let them go, we don't go in and we don't touch the internals. They will kind of rearrange themselves internally in order to complete the task that we've asked them to do. So if this was a machine learning model and I gave it, the appropriate ingredients for bread, because that's important, it can't do it with just anything, can't do it with just gravel and horse manure, it still needs good ingredients. Then what would happen is I would show that model this beautiful piece of bread and say, hey, machine learning model, please use those ingredients to make me bread that looks like this, right? And I hold it up. And it would churn for a minute, and it would spit out a nasty, black, inedible lump. It looks nothing like bread. And then when that happens, I say, bad model, slap it on the wrists. And please try again. And I show it the beautiful bread one more time, right? And it says, okay, I'll try again. And it churns for a little bit while, and it spits out another lump, slightly less black and slightly more loaf-shaped than before. Right? So it's made an improvement, but it's still not right. I say, bad machine, try again, and I show it the good loaf again. Well, this process repeats itself thousands, maybe even millions of times until that model has rearranged its internals just so that those inputs get translated to the correct outputs. And that's really the entirety of a machine learning model's job, is taking the inputs, in our case data, numbers, and turning them into the right outputs. Other numbers, but output numbers, things that we want to predict, right? So it's this fascinating thing where we don't ever deliberately program the internals of a machine learning model to do anything. Through this process of repeated trial and error that sometimes feels like brute force or maybe even just luck, right? Over time, it learns how to make that translation, right? There's a funny famous meme / tweet here that says, today I learned that changing random stuff until your program works is hacky and quote unquote bad coding practice. But if you do it fast enough, it's machine learning and pays 4 times your current salary, right? So this guess and check, this trial and error method is a common process that many machine learning algorithms use to try and be able to translate that data into predictions, inputs into outputs. And as I mentioned, you can't just give the bread making machine whatever you want and hope it makes bread. It can't rearrange atoms. You got to give it good ingredients. You have to give it good inputs. And that's the same with our machine learning algorithms. There's a saying in the industry that says garbage in, garbage out. If I give this model bad data as inputs, it can't make good predictions, right? And that kind of leads to the meaning of the word model, right? What is a model? Well, it's just a computer program that uses algorithms, another a vocab word we'll talk about in a sec, to learn patterns in data and to make predictions about new data, right? So what is the model doing? Well, it's figuring out how to translate those inputs into outputs. It's modeling that. I think I don't love the term model. I think it's too vague and generic, and that's the case for a lot of things in the machine learning world and programming world. If we could call it like a data translator or something like that, I think that would be more a better name for it, right? But its job is to figure out, or quote unquote model, how the input data relates to the output data so that we can repeatedly produce the right outputs when given good inputs, right? Well then, what is an algorithm? Well, an algorithm is a, quote, set of instructions to be followed in calculations or other problem-solving operations, right? It's basically the instructions that we give to the computer in order to tell it how to figure out that relationship between the inputs and the outputs, right? And I have a question for you guys. You can just answer in the YouTube chat if you feel like it. If not, just think about it to yourself, right? What do we do to give a computer instructions, right? What are some of the ways we can give a computer instructions or commands? And there is a few second delay on the stream here, so I'll pause for a minute. One of the things we can do that I think of is we can click on stuff, use that graphical user interface, that GUI. Yeah, Cigar says typing using the keyboard, right? But specifically, if we want to give really specific instructions to a computer, we do type, but what do we type? We type code, right? We write code and we give that code to the computer, and that code is the instruction. So like all that an algorithm is a computer program that on its own can figure out how to translate input data to output predictions. And it's written in code. It's written in Python, most often in the data science world. The vast majority of data science today is done in Python. That may not always be the case, but that is currently the industry standard. And so any code that we write today, we will be writing Python code together. Excellent. Okay. So I want to talk a little bit more specifically about this data we've been talking about. There's a lot of data formats, but one of the most popular ones and one of the best introductory data formats is something called tabular data. The word tabular is related to the word table, right? Data that lives in a table has rows and columns. It's essentially just a grid of stuff, usually numbers, right? A grid of stuff is tabular data. Hopefully it's numbers. We would like it to be numbers as often as possible. Those are the easiest things to calculate stuff with. I'm going to actually break away from the little presentation here because I've got this same tabular data here in a Google Sheet, right? Just a CSV, right? CSV stands for comma separated value, and it's just the raw text format of this data when it's in a plain file, okay? But I want you to notice that we have rows of data. We could view it, the data that way. And we also have columns of data. We could view the data that way. Or we could view it in a grid as a whole. Okay. And those are distinct ways of talking about this data. Now, based on the title here, it says singlefamilyhomes.csv. What do you think an individual row of this data set represents? Any given row. Cigar says one object. Yeah, we call that our unit of observation, right? One thing. Yeah, properties of one object. In this case, these objects are single family homes, right? These are homes that people live in, and so each row is a different home. Each column, as Cigar mentioned, is a property. We also call this an aspect, a feature, an attribute. Those are all synonyms for the same thing of these different properties. Okay. Now, of all of this data, there's typically, we look for one specific column, and we pick that column to be the thing that we want to predict. The thing that we want to predict. So of these 4 columns, which of the 4 of them do you think would be the most logical choice for being the thing that we want our algorithm to predict? What do you think? Cigar says sale price, and I agree. When you're working with real estate data, you're most often trying to predict the price of the property, the sale price, right? Then you can look at current properties that are on the market, compare them to your predicted sale price, and tell if they are overvalued, undervalued. You know, make decisions based off that. Make investments. Know, is it a buyer's market, seller's market, etc. All those things. Technically, it's up to us, the data scientist. We can pick any column we want to be the thing that we want to predict. Okay. But once we've made that decision, then there becomes forevermore a distinction between these columns, right? And they get different names. So going back to our slideshow here, right? The thing that we want to predict is called the target in a machine learning world. It gets actually a few different names, but target is the most common one that I've seen. And then the other columns, those are attributes or features of that unit of observation, right? They're features of homes. Homes have a square footage, they have a lot size, I guess the properties do, and they have a number of bedrooms, right? So the thing that we want to predict is the target. Everything else that we might use as inputs are the attributes and features, right? So even here inside of our data set, we have that input versus output separation once we've chosen what we want to predict, right? What we want to predict is going to be the outputs. We're going to make sale price predictions, and we're going to feed our model square footage, lot size, and number of bedrooms as inputs to the model. Okay, but that terminology is really important. Target and then features / attributes. You can use either of those words. And in fact, there's a lot of other synonyms for the word target. Something you'll hear me say quite often due to my economics statistics background, you'll hear me say Y variable a lot. And in fact, you'll see that represented in some of the code we write a little bit later. We'll call that target the Y variable. So those two are pretty interchangeable. Some of these other ones really depends on the context of the speaker that they come from, right? The dependent variable, output variable, response variable, the predicted variable, experimental variable, measured variable, regressand, outcome variable, explained variable, or just label, particularly if it's this categorical data, right? So I just wanted to make you aware, if you're out there reading stuff about data science, machine learning, about predictive modeling, and you hear any of these terms, they all mean the same thing. They all just mean the thing that we want to predict. That's it. It's a lot of jargon for a simple concept. Similarly, these attributes and features, they also get a lot of different names. Okay? Call them predictors, X variables, independent variables, dimensions, input variables, explanatory variables, manipulated variables, exposure variables, regressors, and observed variables. And notice I made all of these plural because almost always we'll have more than one X variable. We can do modeling if we just have one, but it's kind of boring and not as useful. And so typically we have, right, Typically, we have lots of attributes and features and just one target that we're trying to predict. Okay. So that is kind of an overview of tabular data, an overview of what these inputs and outputs look like. And now I want to talk to you about the most important thing I could talk to you about in all of machine learning. This concept of something we call generalizability is the end-all be-all. It is the entire point of machine learning. And it is the model's ability to make good predictions using input data that was not seen in the training process. Okay. Think with me for a minute. What are some machine learning algorithms, or what is some artificial intelligence that you interact with in your life already? Can you think of any examples? I'll give you a minute to think of some, and then I'll throw in a few that come to my mind as well. Okay. Keep thinking, keep typing. I'm going to just talk over the delay here. Oh, so guys, can you repeat the question? What are some examples of machine learning that you interact with in your day-to-day life? And it may not jump out at you because a lot of these examples they're just part of the fabric of what you do. You don't really notice that they're there. One example is if your phone uses facial recognition to unlock itself, right? What's it taking is the input data. It's taking the shape of your face as its input data. And what is its prediction? Well, whether or not it's you or not, whether or not you're the owner of the phone or not. It's making that classification, right? What about, oh, Cigar says, the most purchased product or sold product on a website, or most preferred, or a famous product. Yeah. Think about if you go to Amazon.com, for example, and you're searching for something to buy, and on all the sidebars, it's customers who bought this also bought, and they're trying to refer you to other products that you might like to buy. Well, they're taking all your shopping data, all your history with them, and trying to recommend to you popular products that you might also be interested in, right? It's taking that input data and it's making a prediction. The prediction is what it thinks you would most like to buy. And they might be right, they might be wrong, right? Caesar the Bengal says movie recommendations. Yeah, all these kind of recommender systems, as we call them, are great. I think that IMDb, the website, has like an okay movie recommendation system. If you go in and find a movie that you already like, you're going to get to see some similar movies to that might also be in the same ballpark. Okay, so these are all examples. Another example is self-driving cars, right? It's taking inputs about the world around it through video and LiDAR, and then deciding as the outputs, what's it going to do to the car? How's it going to move the wheel? What's it going to do to the brake, the gas pedal, etc. Another example is credit card fraud detection, right? You make a transaction, the credit card company's trying to look at the properties of that transaction and say, oh, is this a spam? Is this a scam transaction? Is this fraudulent? Or is this good? Is this a normal transaction? And if it's fraudulent, they may block that transaction, call you on the phone and say, hey, was this you? Something like that. Or even a spam filter on your email decides that something's spam versus not spam is a machine learning algorithm, right? All these things in the world around us that are just, one, computer programs, that two, take in inputs, and three, try to make useful predictions. Okay, so just think about those as we come back to this topic of generalizability. All machine learning models have to be trained. Just like our bread making machine, we had to teach it, hey, that thing you made, that's not what bread looks like. It looks like this, right? And we had to give it correction. And that allowed it to make improvements and make better predictions over time, right? And that whole process of training and the model making better and better and better predictions is really important. But that's not the end goal. The end goal is that the model, when it gets out in the wild, be able to make good and useful predictions on data that it has never seen before, right? A self-driving car can be trained on a whole bunch of different streets, but when your car gets on a road it's never seen before, it still needs to operate correctly. A credit card fraud transaction software needs to take in transactions that it's never seen before, but still know how to handle them, still know how to categorize them, right? So our goal here is not just to give data to a model and hope that it makes good outputs. Our hope is that we can train that model so when it sees new data that it's never seen before, that it will still make good predictions even on that unseen data. Okay? And that is one of the trickiest things about machine learning, is simulating this scenario where we give some data to the model to train it, and then we're going to hold some data aside to test that model or to see if that model generalizes to data that it hasn't ever seen before. And that's one of the things I want to do with you today with code. We'll see a small example of that when we get to the coding portion. Okay? But just remember, the goal is not just to make good or accurate predictions. The goal is to make good or accurate predictions on data that the model has never encountered before. That's the end all be all of this whole kit and caboodle. Okay? We call that process model validation, right? And as I mentioned, we're going to split our data into two portions. At least this is the simplest version of model validation. There's actually a lot of ways to do model validation, right? But we're going to try and simulate the scenario where the model needs to generalize on unseen data. So we'll take the majority of the data and we'll put that in what we call the training dataset. The training dataset. And that's what the model will be allowed to see and train and run on. And we'll hold that test data in reserve, and the model will never touch it until it's done being trained, and then we'll feed it the test data and we'll see if it truly is making good predictions or not, right? So the training data set is going to be the majority of our data. Test data set is a small portion we hold in reserve to validate whether or not our model can generalize. Okay? A lot of maybe new terminology here, but this is all really important, really core terminology to the machine learning world. Actually, before we get into this next section, do you guys have any questions for me? Any questions? Now that we've kind of gone over a lot of that basic terminology, kind of to a new section here, right? As I mentioned in our, forgive my tabbing back, our learning objectives, we've just gone through all of the topics in the terminology section. And now we're going to talk about categories of machine learning models. And then at the end, we're going to actually fit maybe your very first ever machine learning model. I don't know if you've done it before or not, but we'll do it together. Yeah, Cigar asks a really good question. And I might be able to more fully answer this question on Thursday. Sorry, let me zoom back to my next slide here. Yes, when we say training with data, that means exactly what? Do we mean storing some properties or what? Yeah, so our machine learning models, here's a diagram of one. Oh, Gemini, go away. Okay. This diagram here represents a neural network. Okay. And each of these little circles inside of a neural network, it basically holds, well, I take it back. Each of the arrows, each of these lines connecting the circles in the neural network, those represent different numbers. Okay? Each of these lines is a different number. And those numbers decide how does the data flow through the network from input to output. Okay? And as the model trains, those numbers get tweaked a little bit. Every time that I hold up that piece of bread and say, that's not right, model, please make your outputs more like this, the model will tweak its internals, as I mentioned. Basically, every single machine learning model holds some numbers inside of it. And those numbers have different names. They're called weights or parameters. Biases, those are all more or less the same thing. Every single machine learning model holds numbers inside of it, and those numbers determine how the computation happens, how the translation from inputs to outputs happens. And those numbers get tweaked during the training process. As the model gets exposed to a batch of data, the model's going to try and make as good of predictions as it can. And then if its predictions aren't perfect, it's going to go and tweak its internal numbers. And it's going to try and do it again and again and again and again, seeing batch after batch after batch after batch of data. And then after the model's done, after it's able to take any input we give it and make the correct output, then we'll see if we can do it on data that it's never trained on before. So I realize that's still a little bit abstract. Today, we're going to see the minimum amount of code needed, in my experience, to train a machine learning algorithm, a very basic one. And then on Thursday, we're going to dive into the internals of that machine learning algorithm and see exactly how it happens. This introductory algorithm is called a decision tree. And it's one that we should be able to wrap our heads around in about an hour's time on Thursday. So we'll get a lot more deeper into the weeds then. That's okay. I hope that helps answer it a little bit for now. Good question. All right, got about a half hour left. The next thing I want you to make you aware of is that, we talked about all these different machine learning algorithms that we interact with in our daily lives. There's actually a few different major categories of machine learning algorithms. We talk about a few of them today. There's even some more specific categories that we'll talk about on Thursday. These are the big umbrella terms here, and we'll get more into the nitty-gritty next time. But almost all machine learning algorithms can be fit into one of these 4 categories. I want to talk about them with you, so when you hear these terms, they mean something to you, as they are big ideas in the world of machine learning. The first kind of algorithm, first kind of model, algorithm and model are more or less synonymous, okay, is what we call reinforcement learning. These are when the algorithm itself is called an agent, okay, and it makes its own decisions as it interacts with its surrounding world. And as it does so, it is rewarded or punished for its behaviors with the goal of maximizing its reward. Okay? If I tab out here again, I don't know if you've seen these bubble things that are trying to learn how to walk. DeepMind AI learned how to walk. I'm trying to find a GIF. Here's the one that I included in our slideshow, right? Okay, this is an agent. See that it's interacting with its world around it, and the reward that it's trying to maximize is trying to maximize the distance that it travels. And it's detecting the world around it, it's detecting where these red obstacles are and where the gaps in the floor are, and it's trying to go as far as it possibly can. And it just so turns out that if we give it things that look like legs, it will kind of learn bipedal motion just by trying to maximize its reward as it interacts with the world around it. And there's lots of examples of these. There's another one doing bipedal motion and getting lots of obstacles thrown at it. Some of them were wackier than others. But if you've seen a lot of these this has a lot to do with robotics and self-driving cars and autopilots of drones and all those kinds of things. Some really cool things here. Another example that I will share with you is, let's see here. I think this video. I love this video. I think it's a great example.
Each of these cars is controlled by an artificial...
A great example of reinforcement learning. It's using something called a genetic algorithm where they have a bunch of these cars, they have different properties, and they race. And then the top performers from that generation of cars get to pass their attributes, their genes, so-called genes, onto the next generation of cars. And in that way, each generation of cars gets progressively better and better and better at driving. And this is a really good implementation with really cool visuals. That can be a good introduction to reinforcement learning if you're not already familiar with it. There's a lot of video game AIs and things like that that get trained in this way. Why is it not letting me share this? I'll just paste that in the chat. You can go take a look at that when you get a minute. Okay. So that is reinforcement learning. I do not plan on doing a lot of reinforcement learning with you guys, at least in the near future, because reinforcement learning is quite specialized in those areas of self-driving cars and robotics and things like that. And it can be really tricky. So what we're going to be talking about is something called supervised learning. I turn my slideshow back on. Okay. Supervised learning is far and away the most powerful and most valuable category of machine learning models. Okay. In order to do supervised learning, you have to have your target variable included in your data set. Right? So coming back here, our target variable here, sale price, it's in our data set. It gets its own column. It's there. I can see it. I can touch it. I can do things with it. Right? So with this real estate data set, I could use supervised learning on this. If I did not have a sale price column, then I would not be able to do supervised learning, right? So if you want to do supervised learning, you have to ask yourself, is the thing I want to predict, my target, included in my data set or not, right? With our bread making example, that was supervised learning, right? Whenever I held up that good loaf of bread and said, hey, machine, make it more like this, right? That was me supervising the operation of that machine. I was basically giving it correction, giving it feedback that, hey, that prediction you just made, it's not good. It's not like the real true value of that thing. You're far off from predicting what you should be predicting. You gave me a black piece of sludge. It should look like a loaf of bread. Those are not close together. And so the model needs to make big adjustments in order to improve its behavior, right? So with the presence of that target variable, we can give feedback. We can give correction to our model. And I like all those words better than supervision, but that's really what it means. And being able to give this correction, being able to give this feedback to our model is so powerful. It really helps our models improve so much that the vast majority of machine learning that's done today is in this category of supervised learning. And we'll do an example of supervised learning at the end. Okay. You may have heard of some of these Python libraries, scikit-learn, TensorFlow, PyTorch. TensorFlow and PyTorch in particular for doing neural networks. We're going to be using a simple scikit-learn algorithm today. Scikit-learn is more introductory and has more basic, but still powerful machine learning algorithms. Neural networks is where things get tricky and the data sets get huge, and our computers sometimes are not powerful enough to process the things. So we will do some TensorFlow and PyTorch in the future, but for today we're going to look at a scikit-learn example of supervised learning. Okay. But if you hear these library names thrown around, they're almost always doing some kind of supervised learning. Not that they can't do unsupervised learning, which is what we're going to talk about next, but usually not. Okay. Well, what is unsupervised learning? Well, that's when your data is unlabeled, or when there is no target column in your tabular data set. It's not included. So because you don't have that target variable, you can't check your work. The model just does what it thinks is best one time. There isn't this guess and check iterative feedback loop. The model just goes once and says, well, you can't tell me if that prediction is right or wrong, so we'll just hope that that was the good prediction. Without that ability to give correction to the model, unsupervised learning, well, sometimes it's the best you can do. If you don't have that y variable, if you don't have that thing you want to predict, it's all you can do, right? One category of unsupervised learning algorithms that is useful is, for example, clustering algorithms. These are algorithms that try and examine the spatial structure of the data points. How are they related to each other spatially? Like this smiley face you see here, right? This is the result of something called a DB scan clustering algorithm, a density-based scan. And if you click on this YouTube video, which I'll share in the chat as well, you can see a DB scan algorithm in action and see how it decides, oh, this eyeball, that's one cluster, and this eyeball, that's another cluster. How does it decide that? Well, based on spatial proximity to the other points around it. It does make predictions, right? The prediction is, oh, this data point here, what cluster is it in? What group is it in? Oh, it's in the blue cluster. It's in the green cluster. It's in the red cluster. It's in the yellow cluster, right? Those would be the outputs. It's just telling you what group the final data point is in. But there's no way to check your work. There's nothing in the data set that says, yep, that's the right group. You got it right. You just do your best, try and pick the right algorithm, and it gets tricky. Okay? But these algorithms do have a place. They are useful. Cigar asks, what is the use of unsupervised learning? And why do you even analyze the data which is unlabeled? I'm thinking in terms of a practical use case. And your intuition there, Cigar, is spot on. Some of my colleagues have told me that they would prefer to take unlabeled data and go out and pay humans to manually label it so that they can use supervised learning rather than use unsupervised learning. They would rather incur all that cost of doing the manual labeling so that they can use supervised learning over unsupervised. It's that much more powerful. And so you want to use supervised whenever you can. You'll use unsupervised when there's no other options, basically. Well, sometimes also I should say, I don't mean to disparage it quite that heavily. Sometimes you really are interested in the spatial structure of the data points. Think about segmenting customers to an e-commerce website based on information about them, right? You might find that you have a group of customers that are 35 to 42-year-old males who like golfing, and you might have another cluster of customers that is teenage females that enjoy volleyball. I don't know, just random example, right? But you may find that people in particular, when people are your data points, that we have these kind of herd behaviors. We tend to be like each other and to I can't remember the word right now, but to mirror each other's behavior, right? So particularly with market segmentation or customer segmentation, unsupervised learning is particularly useful in some of those applications. Just as an example, I don't want to say that it's not useful. I want to give some examples of where it is useful. Good question. The last category here is kind of weird. It's called semi-supervised learning. And this is where just a portion of your data set is labeled. You have some rows that are labeled, but most of them aren't, usually. And in my experience, this happens when you have a giant data set of unlabeled data, and you want to label it, but it is just way too big to manually label all of it. One example of this that I've seen is NASA had this was a few years back, they had a lot of telescope data, images of visual and radar telescope data of galaxies. And as you know, there's bajillions, trillions of galaxies in the known universe. And so there was way too many galaxies to manually label them. And what they did is they asked volunteers to come to the website, and they would serve up an image of the galaxy and to try and categorize it as barred spiral, irregular, spiral, elliptical, etc. I don't remember exactly the categories, but it was some of these types of categories. And in that way, they were able to label at least a portion of the observations that they had. And that was able to help use those observations as a heuristic to be able to put the rest of their data in, at least in the ballpark. We think that's in the ballpark of a barred spiral galaxy, or that's in the ballpark of a spiral galaxy, right? So that was an example of semi-supervised learning. They had a huge data set. They couldn't afford to label all of it. It was impractical to label all of it. So they labeled a portion of it and then just did their best with that. Not as often not as common of a category as the other three that we talked about, but something that you should be aware of. All right. So that's kind of a wrap up of this intro to machine learning. What we're trying to do with our models, we're trying to get generalizable predictions. And today we're going to be using supervised learning. We're going to be using a scikit-learn algorithm to make some predictions. Any questions before we move to writing some code? And I will share these slides with you when we're done in case you're interested. I don't know if they're particularly valuable, but I find that usually like one or two people like having the slides. So I will link those to you when we're done here. All right. The next thing I want to show you is we're going to be writing this code in what's called a notebook. A notebook is a document that data scientists commonly use for writing Python code and doing some prototyping with machine learning algorithms. So I'm going to copy this link to this notebook into the chat. so that you can write code along with me. I'll also share with you a completed version of this code when we're done as well, in case you are watching on your phone or something at this moment and you can't follow along typing. You will get a completed version when we're done. Okay. But we're going to, in each of these gray boxes is a code cell where we're going to write some code. We're going to load some data. We're going to train a machine learning algorithm. We're going to generate some predictions. And we're going to validate that model. We're going to see how accurate its predictions are on unseen data. Okay, you with me? And when we're done today, I have here on the temzi.com website an assignment for you. And in this assignment, you are going to be doing pretty much exactly the same thing we are doing here, but you're going to do it with a different data set. Okay, just so you get one more repetition with these topics, you get some practice. And I just want to show you that if you're here working on these, at any time you can hit View Solution, and it's going to show you one possible version of the code you could write. So if you get stuck, you can click on View Solution and get some help. If you get stuck, you can also join the Temzi Discord channel and ask questions in there. I'll be in there to answer any questions that you have. Right? But this will be your assignment, right? Shouldn't take you too long. You should be able to directly reference the code I'm about to share with you now to be able to accomplish that. Okay. So we're going to start off by loading. Oh, by the way, if you want your own copy of this, when you view this file, you may only have view permissions. You might need to come and say File, Save a Copy in Drive, and then it'll copy a version for you that you can type in, right? The link that I just shared to this Colab notebook, if you refresh this page, it should update with all the code that I've written. Sometimes it doesn't always update instantaneously. You might have to come and refresh the page if you want to see my code. But if you make a copy, then you should be able to do whatever you want with that copy. That copy will be totally yours. You can delete everything if you want. It's up to you. Okay. Alrighty, so we're going to use a data set, a very, very popular starter data set. If you haven't ever worked with this data set, you will. Something called the IRIS data set. And there's a couple of ways to load this data set. This is a website called the UCI Machine Learning Repository. It's short for UC Irvine, the university in California. And this is the page that hosts the IRIS data set. You can get it in a lot of places on the internet, but this is a good one. If you come here and hit this download button, then that will download a zip file to your computer, which then if you unpack or uncompress or expand or whatever the word is, you'll see two important files here, iris.names and iris.data. Okay? Iris.names document explaining what the different columns of this data set represent. It says there's sepal length, width, petal width, and the species. Because iris is here, they are iris flowers. Iris flowers, okay? And then iris.data is a CSV file, just like we have here, right? It's got rows and columns, and we'll take a look at it as well, right? So if I open iris.data with text edit, you'll see each of these is a row of our data set. Let me make this bigger. Each of these is a row, and then we also have columns. Each comma separated value is a column. So it's got rows and columns. It's a grid of data. This is tabular data. So here in Google Colab, what I want to do is I need to upload that data set to my document here. And I can do that by opening up this Files panel on the left-hand side, and then hitting this Upload button, and then I can select from my machine iris.data. And it should show up over here. If it doesn't, you might need to refresh this panel. But once you can see iris.data over here on the left, you're good to go. Your notebook now has that data set. Okay? And we're going to be working with this data set using a Python library called Pandas. Pandas allows us to load that whole table of data and hold it in one big container. That big container is called a data frame. a data frame. So a data frame is just one other kind of table. But that's what the pandas library happens to call it. So we're going to import pandas as PD here. And let me switch windows. All right. And then we're going to use a function called pd.readcsv and see how so many people have used this data set that Google Colab is trying to like autocomplete the whole thing for me. And we just pass in the file name here, iris.data, just like it we see here. df is our variable here. That's where this table is going to get stored, and df is short for data frame. So I can say df.head, and it will show me the first 5 rows of that loaded data set. Cool. So this should look very familiar. It looks a lot like the data set that we saw here. 5.1, 3.5, 1.4, see those same values here. However, with pandas, we want each of these columns to have a name. It's called a column header. And so we're going to pass another argument here. And that's going to be the names of the different columns. And I will paste this to you in a minute because it's kind of a lot to type out. But they're the sepal length, the sepal width, the petal length, and the petal width. These are just 4 different measurements of these iris flowers. And then last but not least, we have the species. Okay? And which of these columns do you think is going to be our Y variable, our target? Well, it's the species column. We're going to take the measurements of these different flowers and try and predict which species it is that we're working with, right? So I can do look at the species column like this, put square brackets after the df variable, and then put the column header as a inside of quotation marks. Call that as a string. Right? So this is just the species column that I've pulled off here. I can take that species column and I can say, hey, count up all the different values that are inside of that column, and it's going to tell me, oh, we've got 50 of each kind of flower. These are the different species. We've got an iris setosa, versicolor, and virginica. Those are the 3 species of flower. We've got 50 of each of them. So we have a total of 150 flowers. I could also see that by telling the data frame, hey, data frame, tell me, table, how many rows and columns do you have? By saying df.shape. It says, okay, I've got 150 rows, 150 flowers, and 5 columns. 1, 2, 3, 4, 5. So this is some very basics with pandas. I'm going to show you a second way to import this data set just for kicks. I think both of these are useful. So this one here, we're just reference the file name that we uploaded. However, if you are on the internet, say at my folder of data sets, I've got a whole bunch of data sets here on GitHub. And you find the data set you want to work with. Here it is in its comma-separated value form. And then you hit the raw button. I'm going kind of fast here. You might have to review the recording later on. You can grab this URL. Anytime you're looking at a raw CSV in your web browser, you can grab this URL and also put it inside of those quotation marks, and it'll do the same thing. If I were to have done this first, I wouldn't ever have had to have uploaded the file, right? So this is using the file that we uploaded to Google Colab. And this one is reaching out across the internet to get the data set from GitHub. So 2 different ways to do the same thing. On your assignment this afternoon, you don't have to do either of those. On your assignment this afternoon, I've automatically loaded the data set for you here. Okay, so that's why I've said here, this step is already done for you on your assignment. This is how I would do it in Google Colab. Temzi, the website, doesn't have the ability to load files or to reach out across the internet to get files, so I had to prepare it for you. So just know, in a regular data science environment, you would need to load your data set. On Temzi, I have to load it for you, basically. But then everything else after this, you'll get to do on your own. Okay. So the next thing we need to do is we need to divide our data set into that training portion and that testing portion, right? When the model is figuring out how to translate those inputs into outputs, when it's modeling those relationships, it's only going to see the training data. And then once it's done learning about how to translate those inputs into outputs, we're going to see if it really knows what it's doing by checking our work with the test data set. Okay? Typically, we want to make the test data set smaller than the training data set. The majority of our observations are rows of data to be in the training data set. Now, what I'm about to write, this code I'm about to write, I don't expect you to understand right now. We'll talk about it a little bit more later. So I'm just going to say test data set, that's going to come from df.sample. And I want to take some fraction of the rows. I want to take 30%, 0.3 of the rows in my data set and put those as the test data set. But I'm going to add something here. I'm going to add something called random state equals 42. Okay. You can put whatever number you want here, but if you have the same random state as me, your code should be exactly the same. Well, the results of your code. Okay. And what do I mean by that? This .sample method here, it is taking a random sample of the rows of our data set. It's randomly selecting 30% of the rows of our data set. But this random state is making it so that if you use the same random state as me, we're still going to get random rows, but we're going to get the same random rows. So you should get the same random state, the same random sample as I do if you use the same 42 here. Okay. And I've pointed that out in the assignment. Please use the random state in the assignment because I'm expecting you to have exactly the same results as I did when I wrote the assignment. So just be careful about that. Whenever you see random states being used in my code, use it in your code exactly the same. Okay. Then the training data set, we are going to simply remove the rows in the test data set. We're going to take our original whole table and say, hey, for the training data set, give me any of the rows that aren't in the test data set. So taken together, these should be all of the rows, right? 30% into test. The remainder that didn't get put into test go into train. That's what I'm saying here. Okay? I realize that this is a bit of rushed code. We haven't talked a lot about code. We haven't talked a ton about Python yet. So this is probably the most rushed code we'll ever go over. Okay? Maybe I shouldn't say that, but it might be true. Okay? I'm going to look at the shape of these just to make sure that they got divided up appropriately, right? I expect tests to be roughly 30% of the data set. The data set originally had 150 rows, so 45 is about 30%. If this was 33%, this would be 50. But 30%, 45 is correct there, right? So that looks like it's correct. And I'm going to check the same thing just with train. This is just a sanity check, making sure my code has done what I think it's done. Cool. 105 observations here. So the train data set has more rows, more than double the rows of the test data set. Okay. This is all preparation to test the generalizability of our model. Okay. But we're not quite done. We now need to take each of these test and train data sets, and we need to split off our target column into its own container. Okay? So we're going to end up, just like we showed here, with one variable that holds all of the attributes and one variable that holds the thing that we want to predict. And we're going to have each of those for both train and test. So a total of 4 different containers for our data. We're going to have the attributes of our training data. We're going to have the target of our training data. We're going to have the attributes of our test data. and the target of our test data. Okay. So we want to remind ourselves what our column headers are. If I do df.columns, it tells me, oh, these are the column headers. Okay. And I'm going to make an x train and a y train variable. I want to call out right now that this x in x train is a capital X versus y in y train is a lowercase y. This is a convention that comes from linear algebra, where a matrix, a grid of data, is typically represented with a capital letter, but just a single column or row of data is typically represented as a vector with a lowercase letter. Just want to be conscientious of the capitalization here. So the training data, I'm going to grab all of the columns except for the species column. And those will be my X variables. Those will be my features, my attributes. Okay. And then for my Y variables, my target, I only want the species column. Now it looks like I'm missing some square brackets here. Okay. So there's X train and Y train. My training data is now ready. I've split it into, right, training inputs and training outputs. And we're going to do the same thing with our test data. And change this to test. Is train a scikit-learn algorithm? No, we're gonna introduce the scikit algorithm next. What we've done up to this point is just all data preparation. We're preparing our data to hand it off to the scikit-learn algorithm. So right now, X train and Y train, they are just containers that are holding our data. We can give the algorithm those containers in a minute so the algorithm can do its magic. So right here, this is where we're going to use scikit-learn. We're going to make a decision tree classifier, and we're going to train it. And I want you to notice that this is going to take 3 lines of code, a total of 3, to train a whole machine learning algorithm. Okay? The data prep was way more lines of code than the actual running of the algorithm. Okay? So what we're going to do is, first off, we have to, 1, import the algorithm. And we're going to do that by saying from sklearn.tree, import decision tree classifier, capital D, capital T, capital C. Okay. And that just loads it into our notebook so that we can now use it. And then we're going to I would try to say this without fancy words. Make 1 untrained model. Okay, that untrained model is going to be our decision tree classifier. Oh, I don't want to do all that. That's okay. The difference here is, here we're importing it. We just type the name. But when we want to make 1 untrained model, we have to put these parentheses at the end. Okay, these parentheses say, hey, don't just load the thing, but make me one of them. Make me 1 decision tree classifier, and save it to this variable model. Also, inside of these parentheses, I'm going to add a random state of 42. If you add that random state on your assignment as well, you should get exactly the same results that I get. And you'll see that random state of 42 in the solution code as well. And then lastly, we fit the model. Fit and train, training the model, fitting the model, those are synonyms with each other, right? So what do? We give it the training inputs and outputs. What are the inputs? The X variables, the attributes. What are the outputs? Our target, our Y variable, right? We're going to give it the inputs. It's going to make a prediction. We're going to compare that prediction to the correct value and tell the model if it's doing it right or not. But these 3 lines are training a machine learning algorithm to predict flower species based on the flower's petal and sepal measurements. Okay, go ahead and run that. I actually don't, I think I forgot to run this code cell up here. You can tell that because there's no number inside of the square brackets here. So I need to come back up and run this code cell as well. Now the last thing I'm going to do is my model has a built-in capability. It's going to generate some predictions and compare those predictions to the actual values, and it's going to calculate the percentage of flowers we were able to correctly classify. Okay, and I'm going to call this variable DT accuracy. That stands for decision tree accuracy. And I'm going to call this score method, and I'm going to give it the test data now, right? I trained on the training data. I test or validate the model with the test data set. Okay, with X test and Y test. And you're going to see that this model is very accurate because this data is easy to classify. These flowers have pretty marked features. So as I run this here, this tells me I am 100% accurate. My model predicted every single flower species correctly. That is not a common thing in the machine learning world. You usually don't get 100% accuracy. But because this is a small data set, and because these flowers have such distinct features, it makes it easy for the algorithm to figure out, oh, it's got big petals, that must be a versicolor. Right? Oh, it's got small petals, that must be virginica. Right? Something like that. Okay. And as I mentioned, we're going to dive way more deeper into this code. I just couldn't leave you without doing some machine learning today. And I wanted to show you that from a practical perspective, training the algorithm is actually one of the easiest things we do. It's all of the preparation to the data beforehand that is tricky. And a couple of other things that we'll get to, right? Next time we will just dive into the specific operations of the decision tree classifier and really break down, okay, that's an algorithm. What instructions is it giving to the computer? What calculations is it doing in order to take those inputs, X data, attributes, and turn them into good predictions? And even be able to do and make good predictions on data that it was not trained on, generalized to unseen data. And this is a very small and truly oversimplified version of what we're trying to do with machine learning. Train a model, test and see if it works on unseen data. And if it doesn't work well on unseen data, then we got to go back and change some things. We'll talk more about that next time as well. Okay. So if you revisit the link to this notebook that I shared with you in the chat, if you refresh the page, you should see all of the code that I've written up to this point. And you should have that here as a reference and be able to use that reference. I would hope to do some of these exercises on the TEMZ website. Now you will need to be logged in on the TEMZ website because it's going to try and save your work. In case you accidentally leave the page, if you come back, your work should still be there. So it's going to ask you to log in. But I hope that you feel like this has been a good starting place and you're excited to come back on Thursday and learn even more together. Okay. For those of you who maybe got here a little bit late, not a problem at all because YouTube automatically records everything here. I would just remind you of this survey that I would be so grateful if you would fill out for me. I will re-copy the link here. And again, if you have any problems doing these exercises here, join the Discord channel. You can even email me, admin@temz.com. I'll be checking that, or reach out to me on Twitter. And I'm really glad that you came here today. Do you guys have any final questions for me? Oh, one other thing I'll say is that once YouTube has finished with this video, I will add it to the top of this page here, and I'll also add the slides and a link to my version of the lecture code here. I will link to all that here at the top of this file. So for the assignment, we log in and solve it on Temzi? Absolutely. Yep. And your code will end up being very similar to what we did here. In fact, you get to leave out a few of these code cells, but yeah, see if you can figure it out, and we'll dive even more deeper into the decision tree classifier on Thursday. Thanks for your participation. Thanks for being here. I won't hold you up any longer. I'll let you go back your evening. Cigar says, next time, can you share how to use Colab, some basic menus and things, anything we need to read beforehand? Absolutely, I can do that. Another thing I would point you to, there's some content here on the Temzi website. The Temzi website is still very much a work in progress. But one of the things you can watch here is this intro to Google Collaboratory video. This is one of the videos that I actually have done. I have a lot of videos that are like 70% of the way done and are not posted on the site yet. That's one thing you can watch that will also give you an overview of Google Colab as a tool generally. And it'll also make you log in order to watch the video. There's a lot of constraints that the website puts on you, but yeah, I hope that's helpful. Okay. Thank you, everyone. You are awesome. Have a great rest of your Tuesday, and I'll see you same time, same place, Thursday at 8 p.m., where we'll talk more about decision tree classifiers. Thanks, everyone. Have a great evening.